Hey everyone, in today's lecture, we'll be discussing about the measurement of low resistance. For the measurement of low resistance, many different type of methods are available. That is using a Kelvin's double bridge, using ohm meter and using potentiometer. We'll be discussing about Kelvin's double bridge in today's lecture and also we'll be discussing about ohm meter. In ohm meter, we have two different type of ohm meters. That is a shunt type ohm meter, which is used for the measurement of low resistance, and a series type ohm meter, which is used for the measurement of medium resistance. We'll be discussing about both these type of ohm meters. The bridge shown in the circuit diagram is a Kelvin's double bridge. As we know that Kelvin's double bridge, it is a modification of the Wheatstone bridge and it will provide great accuracy in measurement of low resistance value. That is, when we are discussing about low resistance are in the range of 1 ohm. Now even in this range of 1 ohm, if an addition of 0.1 ohm is there, that is almost there is a 10% increase in the value of the final value. Now for example, if I were using medium resistance, now when I am talking about medium resistance, in medium resistance, if 100 ohm was measured and in this 100 ohm plus 0.1 ohm if it is added, it is very low value. Therefore there is no much consideration when I am talking, there is no much consideration of the resistance of the wires that we are using. Here some wires we might be using, here some contacts we might have done. Now all these will have some small value of resistance. Now all these values of resistance are not of considerable value when we are talking about medium resistance measurement and high resistance measurement. But when we are talking about low resistance measurement, the wires that we are using, the connections that we have made, all these will have small amount of resistances, and these small amount of resistances, that is 0.1 ohm for example, let us consider. Now this will make a considerable change to the final value of final measured value. Now what we have to do is we have to nullify the effect of resistance, that is the resistance of wire, maybe the resistance of contact that we are using, maybe the resistance of probes that we are using, maybe the resistance of screws that are used for making connections. All these things, these resistance effects has to be nullified. Now for nullification of that, we are using Kelvin's double bridge, and Kelvin's double bridge is a modification of Wheatstone bridge. Now let us consider a Wheatstone bridge. Now talking about a Wheatstone bridge, this is this circuit diagram of a Wheatstone bridge. Now when we are talking about a Wheatstone bridge, the galvanometer will show null deflection. For example, if the galvanometer is connected here, what will happen? The additional resistance R1, this will get added to this resistance, that is R resistance R1 will get connected. Now if for example, if I am connecting galvanometer here, what will happen? The extra lead that is connected here, this will get added to the resistance S1. So in this manner, small change in resistance will be felt in the measurements that we are taking. So what we have to do is we have to find out a null point in such a manner that in this null point, the resistance, that is extra resistance, whatever is added, its effect should be nullified. Now what we will do is, this is the modified form of a Wheatstone bridge. So as I have told, in Wheatstone bridge we have PQ, that is the ratio arm, we have R, that is the unknown resistance, and S, the standard resistance we are having in the Wheatstone bridge, and a galvanometer we are having. Now when we are comparing a Wheatstone bridge and a Kelvin's double bridge, we can see that a small resistance P and Q is getting added, a small resistance or ratio arm, an additional ratio arm is getting added. That is why it is called as Kelvin's double bridge. Why it is called as double bridge? Because there are two ratio arms connected, therefore it is called as Kelvin's double bridge. Now here we can see the galvanometer, it is connected in between this in between the two ratio arms. Now one more thing to be noted here is that the resistance of the lead wires that we are using is also included here, that is a small r quantity that is shown in the diagram. It shows the resistance of the lead. Now what we have to do is we have to see whether if connecting this, will it have any effect, or can the effect of PQ and R, small r, be that is connecting additional resistances, considering additional resistances, can the effect of lead resistance, contact resistance, can it be nullified or not? We'll try to check it using some numerical analysis. We'll try to check it, and in the upcoming part. Now right now here we can see that the Kelvin double bridge, it incorporates the second set of ratio arms, as I have already told. The first ratio arm is capital P and capital Q that is connected here. The second set of ratio arms is small p and small q that is connected just below the first ratio arm, and a galvanometer is connected in between point B and point D, and we can also see that at between M and L there is a lead resistance R that is connected. Now we have to nullify the effect of this lead resistance. This is the R, that is the unknown resistance value that we are going to determine, and this is S, that is the standard resistance we are going to determine. Now let us look into the calculation part. Now looking into the calculation part, as I have said, there are two ratio arms, capital P, capital Q, small p, small q. Now these two ratio arms, they are selected, the resistances are selected. For example P by Q is 10 by 5. 10 by 5 will give the ratio of 2. So what I will do is small p by small q, it will be selected like for example 2 by 1. This will also give the ratio 2. Now here we can see here, that is the ratio that is formed of P, capital P by Q and small p by Q will be equal. This is the first consideration that we are making. And now when I am talking about the bridge balance condition, we know that this point B and point D, that is bridge balance, means no current will flow across the galvanometer. The current flowing across the galvanometer is 0. Now when this is 0, it means that B and D are at the same potential and A is a common point. So I can tell the potential drop between point A and B and the potential drop between point A and D are equal. Why? Because A is a common point and B and D are at the same potential. Therefore I can say EAB is equal to EAMD, and this is only possible at the balance condition. Balance condition means the galvanometer will be showing 0 deflection. Now I have marked this at equation A. Now moving further, I have to find out the potential between EAB. That is, I have to find what is the potential between EAB. Now when no current is flowing across this, it clearly means that EABC, this is will be having the potential across this. So what we can clearly make out here is that is the potential drop across this point and potential drop across this point will be equal. So what I can clearly make out here is that if I want to find out what is the value of EAB, what I'll do is I'll apply the voltage division rule. So the resistance across this is P, the resistance of the full arm is P plus Q. So I'll have to do P divided by P plus Q into EAC, that is the complete potential across this path. The complete potential across this path is EAC into P divided by P plus Q, that is the total resistance of the path. So I am doing this, I'll getting by applying voltage division rule, I can find out what is the value of EAB. Now I have found out what is the value of EAB. Now when I am looking at this condition, here I can see some EAC is there. Now we will find out what is the value of EAC. Now for finding out the value of EAC, let us look into this circuit. Looking at this circuit, that is A is this point, C is this point, I can clearly make out a resistance R is connected. To this, a parallel combination P, small q and small r, the lead resistance, and across this in series S is connected. Now this is resketched here, that is in between point A and C, I can clearly see that is R, capital R is connected, small p, small q, small r, PQ and R, these are in parallel, and this combination is in series with R and S resistor. So based on that, I know the current I is flowing across this. Now as current I is flowing, to find out what is the voltage drop EAC, I just have to find out the equivalent resistance. Finding out equivalent resistance, I know R and S is in series and it is in series with the parallel combination. So based on that, I am getting what is the value of EAC. I am marking it as the next equation. This is marked as the second equation B. I am getting this as the next equation. Now moving further, I have to find out what is the value of EAMD, because EAB, it is equal to EAMD. Now what is EAMD? EAMD is nothing but the lower arm. Now I have to find out what is the potential drop across EAMD. Now to find out potential drop across EAMD, I can clearly make out this EAMD, two components are connected, that is EAM and EMD. I have to find out these two potentials I have to find out. Therefore EAMD I am writing it to be EAM plus EAMD. Now EAM directly I can find out it to be IR, because current I is flowing and only R is there. Now I have to find out what is the potential drop across EAMD. Now to find out the potential drop across EAMD, this is MD. I have to find out what is the voltage drop across this point EMN. If I am finding out the potential drop across this point EAMN, then I can apply voltage division rule and I can find out what is the voltage drop across EAMD. Now to find out EAMN, this is the EAMN, this is the EAMN point. So I can clearly see that EAMN is nothing but the current I is flowing across this path. So current I into the parallel combination, that is the parallel combination is P plus Q into R divided by P plus Q plus R. Now doing this, I find out what is the value of EAMN. After finding out the value of EAMN, to find out the value of EAMD, what I will do, I have to apply the potential voltage division rule. Applying the voltage division rule, I can clearly make out P, that is for at across point across the resistor R, I have to find out what is the voltage. Therefore P divided by the total resistance of the part, that is small p plus Q. Now applying that, I find out what is the value of EAMD. I am getting the value of EAMD. Already I have found out what is the value of EAMN. I'll substitute it here. Substituting it here, I finally get I into small pr divided by P plus Q plus R. This is the value of EAMD. Now this is marked as the next equation. Now from here, I have understood that is EAMD is nothing but EAM plus EAMD. I have found out what is the value of EAMD. Now I'll substitute this in this equation and I'll get what is the final value of EAMD. I have found out what is the final value of EAMD. Now this is the right hand side of my equation. I found out what is the right hand side of my equation. Now I have to calculate what is the left hand side of my equation. Now I have done half calculation for the left hand side previously I have done. Now in here I can see I have to find out what is the value of EAB. I have already found out what is the value of EAC. Now I just have to substitute here. Now substituting this equation C in equation B, I get the value of EAB. I have got the value of EAB. I have got the value of EAMD. I have all the materials required for substitution in equation A. Now in equation A is EAB is equal to EAMD. I found out what is the value of EAMD and I also find out what is the value of EAB. Now what I'll do is I'll just substitute in the previous equation. Substituting it, I get this equation. Now solving this equation further, I get a term. Solving this equation further, I get a term R is equal to capital R is equal to capital PS by Q plus small qr, that is capital P by Q minus small p by Q into 1 by P plus Q plus R. Now as we were discussing about the ratio arm, we have seen that if the ratio arm is selected in such a manner that P by Q, capital P by Q and the ratio small p by Q, it is equal. Now if its ratio is equal, it clearly means that this term that I am having, it will be 0. Now when this term is 0 multiplied with this and multiplied with this, the complete term will get cancelled out. This will become 0 and finally I will be getting the expression to be R is equal to PQ into P by Q into S. That is the unknown resistance R can be calculated in terms of the ratio arm and the standard resistance value that I am having. Now from this equation it is quite clear that there is no effect of small ratio arm P, small ratio arm Q, small resistance Q and the lead resistance R in the final value of R that we are having. So it clearly means that using Kelvin's double bridge we can eliminate the effect of resistance of the lead resistance in my bridge, or eliminating the lead resistance, I can easily calculate the low resistance value using Kelvin's double bridge, which is a modification of Wheatstone bridge. Now moving further, we'll be discussing about ohm meter. Now when we are discussing about ohm meter, we have two types of ohm meter, that is a series ohm meter and a shunt ohm meter. Now the series ohm meter, we'll be using it for medium resistance measurement and shunt ohm meter will be using it for low resistance measurement. So let us discuss about both the types, right? So ohm meter is an instrument. It is a direct reading device. Why it is called as direct reading device? Because a meter will be there and on this meter some pointer is given, and based on this pointer I can clearly make out what is the value. The deflection of the pointer will give me what is the value of the resistance that I am having. The other methods that we have discussed, that is the Wheatstone bridge, or the loss of charge method that we are having, or the Wheatstone bridge method that we are having. In all those methods we have to make some calculations or some formulas we have to use to find out what is the value of the unknown resistance. But when we are discussing about ohm meter, in ohm meter there is no use of any calculation. Directly the pointer readings, directly it will show what is the value of the unknown resistance that we are connected. Now this instrument, these have low degree of accuracy because the accuracy will depend on it will depend on many factors. That is the accuracy of the instrument, that the measurement instrument of the pointer that we are using. It will depend on all those things, right? Now let us discuss about series type ohm meter. The circuit diagram shown here, it is for a series type ohm meter. Now here we can see that is a basic meter or basic de-Arsonval movement galvanometer is used. A galvanometer is used, and this is connected in parallel with a shunting resistor R2, and this combination it is connected across an adjustable resistant R1 and a battery source E is used, that is EMF source E is used, and Rx, it is the point, that is in between point A and B, the unknown resistance Rx will be connected. Now moving further, we know that the parallel circuit, it is in series with resistance R1 and a battery having EMF E, and the series circuit will be connected across the terminals A and B, and this terminal A and B will be kept open so that some unknown resistance can be connected to find out what is the value. Now as I have said, I am having a scale, I am having, right? On the galvanometer I am having a scale I am having. Now I have to mark the readings or watt readings, because I have to calibrate the scale, because only after calibration of the scale I can make out whenever my pointer is moving. If I am having a calibrated scale, then only I can make out what is the value of the unknown resistance. Now for calibration purpose, what we will do is, we have two conditions that we are having, that is one is short circuit and one is open circuit. Now in this circuit, if I am short circuiting A and B, that is no resistance, Rx is not connected, and I am short circuiting A and B. Now when I am short circuiting A and B, it means that Rx is equal to 0. It is a condition, that is short circuit means the resistance value is 0 and maximum current will flow. That is, the maximum current will flow across this path. Now when maximum current is flowing, it means that the value of Rx is 0. For example, if this is the meter I am having, and if when maximum current is flowing, if meter is coming to this point, this I can clearly mark it, this value of this position to be 0. Now the second condition that I am having is open circuit. Now what I will do is, I will remove this connection. There will be no connection, no resistance will be connected. Now at that condition, what will happen? The resistance value will be infinity. Why it will be infinity? Because minimum amount of current is going to flow. Now the pointer, for example, it will show at this position, so I get the two extremes, that is what is the value of 0 and what is the value of infinity that I am having. Now I will sketch it again. This is the scale that I am having. This is 0 I have got, and this is infinity I have got. Now I have to mark the in between values, right? So in between values, so as I have said, this series type ohm meter, it is used for medium resistance measurement, so I have to mark the in between value. So what I will do is, for example, I will take a 10k resistor, that is already known value, 10k resistor I will take, and I will connect it here. Now when I am connecting the 10k resistor, for example, let me say it is showing this value, I will mark it to be 10k. Then what I will do, I will take a 100k resistor. Now when I am taking 100k resistor, the pointer might show here, so I will mark it to be 100k. So in this manner, what I will do is, all the intermediate markings I can do all the intermediate markings, and the scale is calibrated. Now after the scale is calibrated, what I can do, that is based on after the scale is calibrated, any unknown resistance if I am connecting, based on that what will happen, the pointer will show some deflection. Now based on what deflection the pointer is showing, what I can do is, I can read the value on the scale. For example, if this is 10k and this is 100k, so in between 20, 30, 40, in that manner, some at equal distances I can make some markings, and this will clearly show me what is the value of the unknown resistance that I have connected. So that is why it is said that it is a direct reading device, that is directly it will be reading what is the value of unknown resistance that I have connected. Now let us look at the scale. Now looking at the scale, we can clearly make out this is infinity, this is 0, that is, and this is the mid scale, that is the half scale deflection, that is for half current. When I am passing half current, what deflection it will be showing. Now based on this, I can clearly make out if the value of resistances that I have connected, if it is low, the pointer will move in this direction. If the value of resistance that I have connected, if it is high, this will move in this direction. Now all these calibrations I can make based on known value of resistance that I am having. Therefore it is said that series type ohm meters, it is used for the measurement of medium resistance. Now let us move on to the shunt type ohm meter. Now talking about the shunt type ohm meter, it consists of a battery in series with an adjustable resistance R1 and a basic de-Arsonval meter which is connected in parallel across the EMF E. Now here we can see that the unknown resistance is connected across the terminals A and B. This is the unknown resistance, and it is connected in such a manner that it is parallel with the meter. Now it is necessary to have an on-off switch. Here a on-off switch is necessary because we have to disconnect the battery, because if it is not in use, what will happen? Here the battery will drain out. Why? Because if the switch is connected, this will make a complete path. A complete path will be made here, and the battery will keep on, the current will keep on conducting and battery will discharge. Therefore here a on-off switch is necessary. Now here we can see that if this is two conditions, as in the previous case, two conditions I am having, short circuit and open circuit condition I am having. Now when the terminals AB is short circuited, now what will happen? When the terminal AB is short circuited, it means that the resistance value is 0 ohm. Now when the resistance value is 0 ohm, it means that across the meter no current will be flowing. Why? Because short circuit, all the current will flow across this path, no current will be flowing across the meter. Therefore it means that the meter current value is 0. Now the second condition that I am having is open circuit. Now when this is open circuit, what will happen? It clearly means that the resistance is infinity ohms, or the resistance is infinity for open circuit case. Now here we can see that my current value will be maximum, because when this is open circuit, it clearly means that when this is open circuit, no resistance is connected across here, the maximum current will flow across the current. So based on this, what I can clearly see here is that I can get two conditions, 0 and infinity. Two conditions I can get. Now after that, to mark the intermediate scale, what I will do is, as we know that the shunt type ohm meter, it is used for low resistance measurement. Some low resistance values I will be taking, and based on the low resistance value, what I can do, I can calibrate the scale. That is 1 ohm I'll connect and see where the pointer is moving. I'll connect 10 ohm and see where the pointer is moving. Then I'll connect 0.5 ohm and see, and I'll see where it is moving. So in this manner, some scale, in this scale I'll be calibrating the scale, or I'll be making some markings on the scale. So this will be how the scale of a shunt type ohm meter is seen. So this is 0, this is infinity. So in between some markings are made, these calibrations are done, and based on this calibrations, when I am connecting an unknown low resistance value across the terminals AB, I can clearly make out what is the value of the unknown low resistance that I have connected. So this is basically a ohm meter. That is, so we have discussed here that series type ohm meters, it will be used for the calculation of medium resistance values, and shunt type ohm meters, it will be used for the calculation of low resistance value. So this is the basic diagram, or this is the basic working of a ohm meter, and how a ohm meter scale can be calibrated.